So we're going to get into talking about water and making solutions in this unit, which is Unit 11 for this class. And a big thing is that we're going to focus a lot on water solutions. They are the most common sort of solution out there. So thinking about water, the most important solvent, we've got water everywhere. Things that we already know about water. Well, water is based on a tetrahedral electron geometry. It has 4 areas of electrons around the oxygen, 2 bonds, and 2 lone pairs. And that means that its molecular geometry or its shape is bent. It's like a little V shape, or like we draw it with little Mickey Mouse heads. Water, because of that shape, is very polar. Oxygen is much more electronegative than hydrogen. It has 2 lone pairs that belong just up on this top oxygen, so it has a very lopsided distribution of electrons. It has a partial negative charge on the oxygen and a partial positive charge on the side with the hydrogens. Because it is very polar, it's actually one of the reasons that it has an extremely high boiling point and melting point for a molecule of this size. So just to give you an example of something you might be familiar with, propane. You might not know what propane is off the top of your head, but you've probably seen big tanks of propane gas outside of stores because it's used to run gas grills or gas fireplaces. And so propane is a gas at room temperature. In fact, its boiling point is less than negative 40 C. Negative 40, not positive 40, negative 40 C. And propane is C3H8, so its molar mass is 44 grams per mole, quite a bit larger than water's only tiny 18 grams per mole. So something is interesting about water that it really throws off the pattern of boiling and melting points that we would expect. Another interesting thing about water is that water is less dense as a solid than it is as a liquid. Ice floats. That's actually really strange. Most solid things sink in their liquid equivalent. Which we saw yesterday that water has a quite high surface tension. We were able to build up big domes of drops on top of the penny before the surface tension would finally be overwhelmed and the drop would fall apart. And we know that water is an excellent solvent. In fact, it's called the universal solvent. It's not precisely universal, but it sure does dissolve a lot of things. So when we talk about a polar molecule, we are talking about a molecule with an overall dipole moment. And the dipole moment is that lopsided distribution of electrons. In order to show that on paper, we draw an arrow. The arrow points towards the negative side of the dipole and kind of shows the direction that the electrons are favoring. And the greater that the electronegativity difference is, the greater the difference between those sides, the greater the dipole moment. So because water is very polar, I know that this is very partially negative and this is very partially positive. The less something polar something is, the smaller the partial negative and partial positive charge is going to be. And we also might remember from an earlier unit that some molecules, even if they do have polar bonds, we talked about this a little bit earlier, some molecules with polar bonds are not polar. Carbon monoxide is a polar molecule. It has a polar bond between the C and the O, and it has a net overall dipole that's pointing towards the more electronegative oxygen. Ammonia has a net dipole. It has a lone pair up here on this nitrogen, and the nitrogen is more electronegative, so the electrons are going to be lopsided towards the end, and it will have an overall net dipole. However, not all polar bonds come in polar molecules, because if it is symmetrical, remember, those net dipoles cancel out. So there's exactly as much dipole going to the left as there is to the right on CO2. It is perfectly symmetrical, and so this ends up being a non-polar molecule. So we have to look for polar bonds, bonds between different atoms that are not C and H, but we also have to look at the overall molecular shape. If a molecule is symmetrical, then those net dipoles, they end up with no net dipole because the individual dipoles cancel each other out. It's like playing tug of war with two people of exactly the same strength. In the end, you don't get anywhere. And that's going to help us figure out what we want to look at, which is intermolecular forces, which you can abbreviate as IMF, intermolecular force. Intermolecular forces are like the interstate. The interstate is called that because it goes between states. I-35 starts down in McAllen, but goes all the way up to Minnesota. I-10 starts in Florida and goes all the way to California. It goes between states. That's why it's an interstate highway. These are between molecules. So if I'm going to illustrate an IMF, an intermolecular force, I have to have two molecules. Because they are the forces that are helping hold molecules together, these are the forces that we were playing with when we changed the enthalpy of molecules in a phase change. So forming and disrupting intermolecular forces is what we were actually doing when we melted or boiled or condensed or froze a substance. And the strength of the intermolecular forces between molecules is really important to a lot of the measurable properties of a molecule. Its boiling point, its melting point, its surface tension, its vapor pressure, whether or not it dissolves in a particular solvent. All of these things are really intermolecular force problems. So there are three types, or I like to say 3.5 types of intermolecular forces. The first type is a dipole-dipole force. That is between two permanently polar molecules, partial positive and partial negative charge. Remember, Coulombic attraction, the first semester answer to many, many things in AP chemistry, is plus minus charge attraction. If a molecule has a permanently partially positive charge, it will be attracted to the partially negative charge on another molecule, and that attraction will help hold that molecule in the liquid form and might help hold it together as a droplet. A special case of that is called hydrogen bonding, which we'll talk about more in some detail in a minute. An ion dipole force is a force between a polar molecule and an ion. Think about salt water. These are very strong attractions because they are not dealing with a partial positive and negative charge. They're dealing with a fully charged ion and the partial charge on another dipole. And the last one would be London dispersion forces. London dispersion forces are found between all molecules, and they are these very fast interactions between the electrons between two different molecules. And London dispersion forces have everything to do with surface area. The more surface area molecules have to interact with each other, the stronger the London dispersion forces are going to be. So let's get into these types in some more detail. So as I mentioned, dipole-dipole forces. These are between two permanently polar molecules, something like HCl. HCl is a polar molecule. There's a lot more electron density around the more electronegative chlorine with its 3 lone pairs that just belong to it. And so there is a plus-minus charge attraction between the partial negative on the chlorine and the partial positive on a different H. Notice there is a difference between the covalent bond that is intramolecular, inside the molecule, and the intermolecular force between two molecules. And so in order to show that that's different, we show that strong shared electron covalent bond as a solid line and the intermolecular attraction as a dotted line. And compared to any covalent bond, an intermolecular attraction is super weak. Covalent bonds are much, 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 much stronger than intermolecular forces. So a dipole-dipole force requires you to have two polar molecules. Then they are able to interact with the plus, minus, partial negative, and partial positive charges. Hydrogen bonding is a special case of dipole-dipole forces. That's why I say it's kind of a half of a different kind of force, because it's just a special case of dipole-dipole. The thing is, I would love to go take Linus Pauling, who came up with this term. I would love to take him out and have him a good stern talking to, because I hate the term hydrogen bonding, because it sounds like I should be talking about this, the bond between the O and the H inside water. That is not hydrogen bonding. That is a covalent intramolecular bond. Hydrogen bonding is an intermolecular force. So it is between two different molecules. So here, these intermolecular dotted line forces, those are hydrogen bonds. I like to call it the hydrogen bonding force, just to kind of keep reinforcing in your head that the hydrogen bonding force is an intermolecular force. It is not a covalent bond. Hydrogen bonding is only found in 3 cases: when the hydrogen is directly bonded to fluorine, to oxygen, or to nitrogen. Those are the 3 most electronegative elements on the whole periodic table. So these are the 3 most polar bonds that I can make with hydrogen. So they are the 3 most partially positive and partially negative, strongest charge bonds that I can make. And that's why they have such a strong plus-minus attraction to other molecules that way. So hydrogen bonding is really important in a molecule like water, because this is just a very simplified picture. All of these molecules can also be attracted, say, this hydrogen can also be attracted up here, and this one could also be attracted over here. So it's like a big net of hydrogen bonding interactions. But if you think about having a strong intermolecular force acting like a big fish net all through around and these different molecules, you can start to see why this is going to be really important in the properties of water. And it's not just water. What actually holds DNA strands together is hydrogen bonding forces between the base pairs. And your body takes advantage of that. You can see on these base pairs, there's lots of hydrogens directly connected to nitrogens. So that's all different locations where I can have some hydrogen bonding. And so what really happens here is that your body and all of its enzymes involved in DNA replication or transcription are taking advantage of the fact that there is this super strong covalent sugar backbone that holds those base pairs in order. But then there is a weaker force that allows them to unzip. The hydrogen bonding between them is not as strong as a covalent bond, so it's easier to unzip those molecules, and unzipping the molecules doesn't have enough energy to disrupt the phosphate backbone. So when they say it's like a zipper, it really does work a lot like that. There's the little teeth that fit together, and the zipper can separate the little teeth, the little hydrogen bonding teeth, but it doesn't actually pull apart the zipper from your jacket, because that is sewn in with strong stitches, not just laced together with a little interaction. So hydrogen bonding is not just a water issue. It is important in lots of other things, especially in biology. It's really important in the structure of proteins as well. If you remember from bio, hearing about the different levels of structure in a protein, several of those different levels of structure, like the alpha helix and the beta pleated sheet and the quaternary structure of enzymes, hydrogen bonding has a lot to do with that as well. So this might look like a familiar diagram because this is the ion dipole force, and we talked about this a little when we talked about salt water yesterday. Now, ion dipole forces are exactly what they sound like. They're between an ion, which is fully charged, a partial, and not partially charged, but a positive charge or a negative charge, or 2 plus and 2 minus, whatever. Because it has a charge, it can kind of weave its way into that web of hydrogen bonding interactions by having the negative sides of water pointing at the positive ions. And then see, this water molecule would also still be able to form a hydrogen bond here, and this one would be able to form a hydrogen bond, and this one could interact with this. So it just fits into that network of plus minus attractions. And in fact, it can even make it a stronger plus minus attraction because it's got a greater amount of charge involved. So ion dipole forces are some of the very strongest intermolecular forces. So we talked about dipole-dipole forces and hydrogen bonding, the special case of dipole-dipole. We talked about ion dipole forces, but what if my molecule isn't polar at all? What if it doesn't have a permanent dipole? What if it is not naturally lopsided? Well, we have a case for that too. And in fact, London dispersion forces are found in all molecules, whether they are polar or nonpolar, or even really whether they're ionic or covalent. London dispersion forces are always found in all molecules. So if anything ever asks you to list intermolecular forces, London dispersion force is always the first one you put down because you know you'll be right. Then you can look and decide if your molecule is polar or not, or has ions or not, and then you can make decisions after that. But all molecules, all compounds will have London dispersion forces. The way I like to explain London dispersion forces is I like you to imagine that you're going to your friend's birthday party. If you're going to your friend's birthday party, when you walk in the door, you're going to be looking around for your friend to say, hi, I'm here, and maybe give them their birthday present. But while you're walking around, you're probably going to see other people that you know. So you might walk by someone that you know from chemistry class and be like, oh, hey, what's up? How'd you think about that quiz on Friday? Oh my gosh. Or, oh, did you finish your lab yet? We should make sure we turn that in. Right? Sure, I'm sure you're talking about chemistry. But when you interact with that person, you don't latch on to them and then just stay there for the rest of the evening. That would be creepy. You just interact with them briefly, and then you move on and you see someone else and you ask them about their math homework, and then eventually you see your friend and you say hi to them. But even though you wanted to come see your friend, you don't spend the whole evening stuck to your friend either. You interact with lots of different people. And so this is kind of a similar thing. A molecule gets close to another molecule, and their electron clouds push on each other, and they make what's called an instantaneous dipole because their electron clouds repel and push on each other, and that makes it lopsided. It's like pushing down on a pillow. When you push down on a pillow, the other side of the pillow pushes up, and that makes that instantaneously lopsided, but it doesn't stay lopsided. Just like you don't stay latched on to the first person you saw at a party, you go talk to other people. When those molecules move away from each other, they go back to being evenly distributed. So it's what's called an instantaneous dipole, but it is reversible. They interact and then they go back to being a regular symmetrical distribution. Now, if you watch some things on the internet or some things in textbooks, a lot of times they will say that London dispersion forces are very weak, but that's not entirely true. London dispersion forces can be incredibly strong forces. And if you really want to think about it, you can think about it by thinking about fats and things that you find in your kitchen. Long chain fatty acids, long saturated fats are things like you find in butter or in animal fat. And those things are solids at room temperature. And that means that there is a lot of inner force in the interactions between those molecules, even though they are nonpolar. Where water, even though it has super strong hydrogen bonding interactions, is already a liquid at room temperature. So sometimes London dispersion forces, if there are a lot of electrons and large surface areas involved, London dispersion forces can be very strong. It's just in small molecules, they often are not very strong. And if I'm trying to compare something like water, which has hydrogen bonding forces, the contribution from a London dispersion force is not that much. That's why sometimes people say, oh, they're just very weak. So as I mentioned, hydrogen bonding is probably the most important intermolecular force in water. And really, it is the answer to why is water weird? All of the weird things that we talk about with water, all of the unusual things about water are really entirely to do with the hydrogen bonding forces between those molecules. For example, because they have super strong intermolecular attractions, that means that it's very difficult to disrupt the solid water and get it to flow because there's a strong force holding it together as a solid. And that means that the melting point is very high. And then it takes a lot of energy to disrupt those potential energies. So the enthalpy of fusion is pretty high. If I look at the boiling point of water, it takes a lot of energy to get the water molecules moving fast enough because they want to stay stuck close to each other. So it takes a lot of energy to heat up water. Remember, it has a freakishly high specific heat capacity because of hydrogen bonding. And then it has an enormous delta H of vaporization because it takes a huge amount of energy to disrupt this strong force and completely get those molecules apart from each other when they're trying to cling to each other with this strong attraction. And it's like your friend who's dating that new guy and she just wants to hang out with him all the time. And you're like, can we just go spend some time together? They're super attracted to each other, so they're like stuck to each other like glue. And you're going, that's kind of the same thing that's happening with water molecules. They have such a super strong attraction to each other that it's really, really hard to heat them up, make them move faster, and then really, really, really hard to separate them entirely and throw those water molecules out into a vapor state. And if you can kind of think about that network of interactions in water, you can start to think about why water has such a very high surface tension. Remember, surface tension is a force that pulls the surface close together. It wants to be the smallest size it can be. So the higher the force of attraction between molecules, the stronger its surface tension can be, which means since water has such a very high surface tension, it's because of its very strong intermolecular forces. And what is that very strong intermolecular force? Hydrogen bonding. Did I mention that everything weird about water has to do with hydrogen bonding? This is yet another case. Speaking of surface tension, that force of attraction, the web of hydrogen bonding forces amongst molecules like water, causes that very high surface tension. And in fact, if there were no gravity, water droplets would actually become a sphere because a sphere has the smallest possible surface area for a given amount of stuff. Actually, you can see this with some experiments that were done on the International Space Station. You can see even the small droplets that are made there become a sphere.
Oh, we made it out the other side. It was a little too hard. That is wild.
There, I think it's gonna stay in now.
Yeah, but it's gonna get it from going back down.
Okay. What else can we get inside there?
Isn't that neat? When you can really see how that surface tension holds that whole bubble together. And in fact, it is so attracted to itself that it can even support the weight and the mass of that camera inside it, so that you could actually see from the GoPro view from inside the droplet out at them taping it from outside. So another odd thing about ice I mentioned is that ice floats in liquid water, and most substances will sink in their liquid form as they are cooling. However, anything that floats in water, including ice, floats because it is less dense than water. That's how boats work. If they weren't full of rooms and air, a boat would not float if it was just a cube of metal. The density of water is 1 gram per milliliter, but in fact, as it gets cooler, it does get more and more dense until I get to the point of maximum density right above the boiling point, the melting point, at about 4 degrees. And you would think that as it gets colder and colder and slower movement, the water molecules would get closer and closer together until they would start to touch each other and begin to vibrate. But the problem is that these partial charges, well, like charges are going to repel each other. Unlike charges attract, but like charges repel. And so eventually these water molecules get so close to each other that the like partial positive charges will repel each other. Partial positives will repel other partial positives, and partial negatives will repel other partial negatives. And so it actually keeps the molecules a certain distance apart once they actually start to settle into a place where they just vibrate instead of rotate and move and tumble. In fact, when water does this, it actually forms these little kind of hexagonal shapes. You can see the hydrogen bonding is again denoted by these dotted lines in between the molecules. And if you've ever wondered why it is, snowflakes always have 6 sides. This is why. Ice forms hexagonal structures held apart by the repulsion between the like partial charges and the attraction between the unlike partial charges. So hydrogen bonding is really part of the reason that water is also less dense as a solid than a liquid. As I said, just about everything weird about water can be explained by talking about hydrogen bonding. That's just a little meme. It amuses me. I always throw it in there just for fun. And so here are some other things that we talked about a little bit when we were talking about the Penny Lab in a little bit more detail. Hydrophobic versus hydrophilic. Hydrophobic is water-fearing, things which do not interact with water well. So when we're thinking about things that generally don't interact with water, we're thinking about things which are non-polar, and therefore they can't get into that web of hydrogen bonding interactions. Those hydrogen bonding interactions get disrupted by something which is hydrophobic. And so something which is hydrophobic will actually be pushed out of that web of hydrogen bonding. And that's why oil, for example, floats on top of water. It's energetically more favorable to push those hydrophobic molecules out of the web of interactions and just have them sit on the top. That is one way to really predict whether something is going to be soluble or insoluble in a solvent or a liquid, is to look at how it could form interactions with the bulk of the solution. This is also how soap works. We talked about this a little bit in the Penny Lab. Soap is a molecule that has long nonpolar chains of C's and H's, and then it has a hydrophilic carboxylic acid head. And so that hydrophilic part of it can interact with water. In fact, the structure of carboxylic acid allows it to form hydrogen bonding interactions with water. And so the hydrophilic part of it can mesh into that network of interactions in the water, but the hydrophobic CH chain cannot. And so what happens when you have a molecule like that is you form what's called a micelle, where the polar part of this, the head group that can interact with water, stays and points out and mixes into that web of interactions. But then the inside of it is all these non-polar groups pointing in towards each other. And this is really one of the ways that they hypothesized that cell membranes got started in biology, is because molecules like this would group together just like they do in our cell membrane. Our cell membrane is a double-sided lipid layer. It's a lipid bilayer. So it's like it formed a micelle where we have the polar hydrophilic side on both sides pointing out like a wall as opposed to a little circle. So this is a very common detergent, sodium dodecyl sulfate, SDS. This is what we call an amphipathic molecule. Two sides coming together, a polar side with the sulfate and a non-polar side with all these C's and H's. So any dirts and oils that are non-polar gets caught up inside this micelle and then is able to wash down the drain because it's inside all these hydrophilic heads. All right, so I'm going to have you start by writing down a bit of vocabulary here, and then we will get more into depth with this in our next video. So soluble versus insoluble. Obviously, soluble is something which can be dissolved. We've talked about this before. Something which is insoluble does not dissolve. So a soluble substance will dissolve and disappear into the solution. An insoluble substance will just sit at the bottom of it or float on the top of it. It just sits. When I say solution, that's a word we've heard of before. A solution is a homogeneous mixture of two or more substances in the same phase. We did talk about this back in first semester. You can have a gas solution like the atmosphere. A solvent is what does the dissolving. So in most solutions, water is our solvent. And the solute is the solid that gets dissolved. So if I'm making salt water, salt is the solute and water is the solvent. And when things dissolve, they do so in two steps: dissociation and solvation with an O. Dissociation is when the solute molecules, or ions, are actually moved apart by the solvent molecules. So if it's an ion, we're actually going to break the ions off of the crystal and move them out into solution as separate dissociated ions. If it is a molecular substance, we're going to break off individual molecules and get them floating out in solution. And solvation is when these solvent molecules are going to form those interactions with the solvent and the solute, and those solvent molecules surrounding the solute are going to keep those molecules from just clustering right back onto the crystal, because they'll be surrounded, forming ion-dipole or dipole-dipole interactions with water. So when we want to think about whether something will dissolve or not, it's important to think about, is it something that will form an interaction with water? If it is something that is polar, it could form a dipole-dipole interaction when it is solvated. If it is something that is ionic, then the ions could form ion-dipole interactions when it solvates with water. But when something is non-polar, it can't form those stronger intermolecular attractions with water. It would only be able to form relatively weaker London dispersion interactions. And so something which is non-polar really can't get into that web of higher, stronger energy interactions, because the only options it can make are these weaker interactions. So they can't really shove their way in with those water molecules. Like, they don't have pokey enough elbows to get through the crowd. And that's going to be really important to think about tomorrow when we look at solvents and solutes. We do a little investigation where we look at what different solvents can be used to dissolve different solutes. So make sure you have this vocabulary down. We'll talk quite a bit more about dissociation and solvation tomorrow when we do our next set of notes on Thursday. But we definitely need to have the difference between the solvent and the solute down before tomorrow's lab.